The Steel Structures Education Foundation is an organization established to foster increased awareness of steel as a building material and to expand the knowledge and understanding of the use of steel in construction. We are proud to present this steel construction story. The urban landscape of the 20th century. This is how we tend to imagine it, a landscape dominated by multi-story buildings. But the reality is quite different. Many buildings in the urban environment are, in fact, single-story structures. In this video, we'll look at the design and construction of the single-story building. We'll examine the vertical and lateral loads which these buildings must carry, and we'll look at the structural systems used to transfer these loads to the building foundation. In Canada, snow is likely to produce one of the most severe loading conditions. Snow can pile up locally, especially where there are changes in roof elevation, as simulated in this model test. Rain can be trapped in the snow, adding additional load. It's no wonder, then, that structural failure in building roofs is most frequently found under snow load conditions. Rain must also be considered as a separate load source. Some municipal bylaws restrict the volume of rain runoff from building roofs. Thus, design for water retained on the roof may be a consideration. Ponding of rainwater on a roof because of roof frame deflection can also produce heavy loads. Drains at low points and roof stiffness to avoid excessive deflection will therefore also be design considerations. To carry roof loads due to snow and rain, sheet steel is the first line of defense. It's used in this way. A coil of sheet steel is roll-formed into a roof deck profile, one chosen by the designer from a number of standard profiles. A flying shear is used to cut it into lengths suitable for the project. The choice of profile is usually based on deck span, thickness of sheet steel, and loading on the roof. The roof deck is supported on open web steel joists, or joists as they're known. Each joist manufacturer uses his own proprietary designs, selecting components to comply with performance criteria specified by the building designer. Production on an assembly line basis explains the economy of joists when many identical members are required. But what about non-typical areas? We talked earlier of local roof loads created by snow pileup. One solution to this problem is to design a joist with a larger capacity to support the additional loads and space the joists at the normal spacing. However, it should be remembered that when a small number of joists are used, the efficiency of production is substantially decreased, driving costs up. Therefore, it may be more cost-effective to reduce the spacing and use joists of the same size used in other areas of the building to produce the necessary load capacity. Reducing joist spacing also reduces the roof deck span. This will increase the load capacity of the roof deck and thus avoid the need for a change in deck strength in areas of heavier loading. At this point in our story, we've looked at roof deck and joists, how they are manufactured and how they are used to support roof loads. Now, let's turn our attention to girders, the primary members which support the joists. Many girders are designed as cantilever girders, also known as Gerber girders, after Heinrich Gerber. Gerber used the concept in European bridges more than a century ago to achieve some of the benefits of continuous girders, with the structure remaining statically determinate. In buildings, girders are continuous over adjacent columns, with simple span drop-in segments attached to the ends of the cantilevers. Continuity over the supports reduces deflections and simplifies connections. This system is also economical in terms of material savings and simplicity of shop fabrication and field erection. When considering this type of design, one subtle but very critical fact must be recognized. The maximum bending moment under uniformly distributed loads frequently occurs over interior columns. This point of maximum negative moment coincides with the maximum shear force in the girder. Thus, stability of this girder column joint is an essential consideration in the design of the girders and the columns. When roof loads are low, as they are most of the year, the assembly, as illustrated, may remain stable. However, as loads increase, there is a tendency for the bottom flange of the girder and the top of the column to move laterally, creating a potentially unstable condition. Let's look at the framing details for a solution to this problem. Loads are transferred to the girder top flange from joists. Good practice dictates that there will be a joist at or near the column. An extension of the joist bottom cord may be used to tie and stabilize the girder bottom flange, thus stabilizing the top of the column. An alternative to bottom cord extensions is to place stiffeners on the girder web above the column. They may be sized to provide column continuity, joint stiffness, and thus joint stability. Designers frequently combine these two systems for simplicity in design, construction, and additional safety. We've looked at the primary and secondary roof framing members, which carry loads to the columns. Now let's look at the columns themselves. First, we'll deal with interior columns. These columns are normally designed as axially loaded, pin-ended members, which are laterally unsupported along their length. Their design length is approximately the same on both principal axes. Because of this symmetry, and because they are loaded as pure compression members, square, hollow structural sections are usually the most economical choice. Now let's consider exterior columns. A new set of design criteria is often involved. First, there are wind loads on the exterior of the building to consider. Wind produces loads on both windward and leeward faces of the building, as well as uplift forces on the roof. The building walls may be capable of spanning from foundations to the top of the building, thus distributing wind loads in more or less equal shares to the roof level and to the foundations. In such cases, the exterior columns can function primarily as axially loaded members. Much more frequently, however, the wall consists of cladding attached to the exterior columns. Wind loads on the cladding are locally transferred to secondary framing members known as girts, and in turn from the girts to the exterior columns. Let's take a closer look at the girts. Girts are used in a horizontal plane, with their spacing often determined by the load capacity of the cladding panels used. The columns then must support both wind loads on the wall and axial loads from the roof. In many cases, girt loads will be applied to the columns through attachment to their outer flanges. These horizontal loads may reverse depending on wind direction, making it necessary to consider stability of the inner column flange. With a requirement for both axial load capacity and bending capacity, a column with greater strength on its primary axis, such as a wide flange column section, will usually be chosen. The spacing between primary exterior columns is usually a reflection of the interior column grid and may be too great for economical spans of the wind girts. Therefore, secondary columns may be introduced between the primary columns to reduce the span of the girts. These additional columns are known as wind columns. In fact, they might well be referred to as wind beams because their major function is to resist horizontal loads from the wind girts. Up to this point, we've looked at the main framing elements used in constructing a single-story building: the roof deck, the joists, girders, interior and exterior columns, girts, and wind columns. Now let's see how these framing elements work together in tandem with the bracing to resist horizontal loads due to wind or earthquake, and of course to provide overall building stability under gravity loads. Loads at the bottom of exterior columns are transferred directly to the foundations. Loads at the top of the exterior columns must be resisted at the roof level. The designer must find a way to distribute these horizontal loads at roof level to bracing elements, which quite frequently can only be accommodated along the perimeter of the structure. The question then arises, how are loads transferred to these isolated elements? Use of the roof as a structural diaphragm is the most common means. A steel roof deck, along with joists which act as stiffening elements, form this structural diaphragm. The diaphragm must have the capacity, both overall and internally between adjacent elements, to transfer forces across the width of the diaphragm. In addition, the boundary of each diaphragm must have sufficient connections to transfer forces through the bracing elements to the foundations. In some cases, a steel deck diaphragm may not be capable of distributing forces applied on the building. A bracing system in the plane of the roof is then used to supplement the diaphragm locally, where stresses are high, or to replace the deck diaphragm. Now that we've examined loads and the components which support these loads, let's look more closely at actual site construction. The building contractor will construct footings to plans and specifications, complete with anchor bolts. The shop-fabricated columns with base plates attached are erected and shimmed to correct elevation, ready for grouting. As an alternative, leveling plates are installed and grouted prior to column erection. After several columns have been bolted down, the cantilever segments of the girder system may be erected. The drop-in spans are then added to complete the lines of primary framing elements. Usually a tie joist, that is a special joist with a bottom chord extension, will be placed on the column grid lines. This bottom chord extension is used by the erector in plumbing the frame. Earlier we talked about the large negative bending moment at this point in the girder. This critical location in the frame is stabilized by connecting the joist bottom chord, thus ensuring stability of the girder bottom flange and the top of the column. After the girders are placed and stabilized by the tie joists and plumbing cables, bundles of open web steel joists may be placed on the frame. Here they are spread to the specified spacing, where they are attached to the girders, usually by welding. Bridging is then installed to brace the joists. The joists and the girders are two elements in the roof system. The third structural element is the steel roof deck. The deck is installed by placing panels side by side on the joist top chords. Each panel is welded or mechanically fastened to the joists. Side seams are connected for vertical load carrying capacity, with additional connections for roof diaphragm capacity if required. Now for a closer look at the building wall. Various forms of wall systems may be used. Wall panels may be factory manufactured and shipped to the site in large elements. Alternatively, the wall system may be field manufactured, beginning with a liner sheet attached to the structural girt system, followed by the installation of subgirts, insulation, and the exterior finish panels. While the installation of the wall cladding is taking place, one other construction process is underway: the completion of the roof system. In a commonly used roof system, insulation is placed on the roof deck and connected to the deck to prevent wind blow-off. The thickness of roof insulation may vary depending on the temperature requirements of the occupants and the energy conservation philosophy of the owner. Insulation is followed by a waterproof coating, usually asphalt paper applied in several layers, with hot asphalt as a bonding agent and protected by a layer of fine gravel. In this program, we've examined the structural elements used in constructing a single-story building. We've seen how each of these framing elements plays a key role in transferring both vertical and lateral loads to the foundations. And we followed their assembly into a cohesive design, which ensures stability of each framing component, as well as overall stability of the building. Finally, we've seen the frame enclosed with its architectural finishes to complete the creation of a new workspace. Each structural element complements another, often acting in a dual capacity. Architectural finishes may also contribute in a structural function. This is the engineering challenge of the single-story building, a challenge to produce a highly optimized, yet repetitive and economical design. A challenge to produce yet another functional, attractive building in our urban environment.